Hello physics enthusiasts, welcome back to this slice of physics, which I believe might be the last one for the algebra-based introductory physics series that I have created. I hope you've enjoyed the journey, and I hope you appreciate that physics is just a tool to explain our observations in the real world. So in this video, we're going to talk about image properties using ray tracing, building on our previous video where we discussed the basics of ray tracing. We will see how the same converging lens can form images of different properties simply based on the distance of the object from the lens. We will see that sometimes we'll get real and sometimes virtual images, so the type can be different. The position of the image depends on the distance of the object from the lens. The orientation of the image can be upright or inverted, and the size can be magnified the same size or smaller than the original object. This will lead us to talking about the magnification equation and the thin lens equation. All right, in this example, I'm taking a converging lens. So here's my lens plane. Here are my focal points on the left side and on the right side of the lens, and the focal length is given by the distance from the lens plane to those focal points. So I've got f on that side and f on this side, and both of these focal lengths are the same. It's a symmetric lens. And here's my optical axis, and here's my object. I've taken an object of height h at a distance of s from the lens plane. And in this example, I've taken s to be 2f. So it's twice the distance from the lens plane as the focal length is. So in order to see where the image will be formed, what type it is, and whether it's upright or inverted, we will use our three principal rays we discussed in the previous video. So the first one will go parallel to the optical axis from the tip of the object, and as a result of that, it'll bend and go through the far focal point. So that'll be my first ray. Because my hand-drawn lines are not straight, I'm going to replace them with straight lines. So here's my first principal ray. The second principal ray I'm going to take is from, again, the tip of the object through the near focal point. So that line, and then you know that that line ends up becoming parallel to the optical axis after passing through the lens. So it'll go something like that. And now I have the position of the tip of the object for the image. It's going to be here. Two lines are enough to see where they intersect. But a good check, because we have three principal rays, it's always good to use all three to make sure that the third one also passes through the same point. If it doesn't, then we made some mistake in drawing one of our rays, and we can go back and check our work. But the third principal ray is the one that goes straight through the very center of the lens, and it continues straight without bending, and it passes through the same point as before, so we are good. And separately, if you take the center point and do the same principal rays, you will find that the image of that point exists somewhere here. If you take the very bottom of the image, you will find that it exists over here. So when you complete the full story, your image will be formed here. So let's discuss the image properties. So in this case, I have a real image. And the reason I have a real image is these are real rays of light that are passing through the point where the image is formed. It's not something that I had to extend backwards for a diverging set of rays. Secondly, we can see clearly that it's inverted. It's not the same orientation as the object, it's upside down. And then we got two other properties to discuss, the image distance and the image size. So in order to do that, let me expand this, and I'm going to clean up some of the previous marks, and we'll continue our discussion. So this is the same picture as before, but I've just zoomed in. And so this S is 2F, this here is F, and the object height is H, the image height is H prime, and the image distance from the lens plane is S prime. So just using simple geometry, we can see that here we have two lines intersecting, the horizontal line that's the optical axis and the ray of light that is passing through the near focal point. So this angle theta here will be the same as the angle theta here, just the law of opposite angles when two lines intersect. And this here is simply S minus F. S is the total distance from the object to the lens plane. F is the distance from the focal point to the lens plane. So what's remaining here is S minus F. And in this particular case, when S is 2f, I get 2f minus f, which is just simply f. So in this case, I got a symmetry. I've got the same distance f from the object to the focal point, and then the same f from the focal point to the lens plane. So that tells me, just based on the triangles, this triangle and this triangle are congruent triangles. They have the same angles and same sides. So that tells me that this here is going to be h also. So the base here was f, the base here was f, the angle is theta in both cases, so the opposites have have to be the same, so it's h. So in this particular case, the image size is going to be same size as the object. Remember, the line that goes through the near focal point is the one that defines the size of the image because it's parallel to the optical axis after this. So regardless of where the image is formed, whether it's formed here or wherever, the size of the image is determined just based on this single line. So I've got size same as object, and then for the position, now I can look at this other triangle, the triangle from the top of the object to the center, very center of the lens. Compare that triangle to this triangle where I have S prime as the base here. So this base is S prime and the opposite is H prime, and this angle, let's call this beta, is going to be the same as this angle beta. So we always have a relationship that H over S equals H prime over S prime because both of those are equal to tangent of beta. And in this case, since H is the same as H prime, S will be the same as S prime. So for position, I will have same distance as object from the lens. Okay, so we took a very symmetric example. When the object is 2 times the focal distance, everything is symmetric. The size of the image is the same size as the object. The position of the image is the same distance on the other side of the lens as the object was on this side of the lens. And then we saw that the image is real and inverted. So just quickly to show you how the sizes can change, if I move the object closer in, so let's say I move it here. So now my S is between F and 2F. So in that case, you can see that this line that goes through the near focal point will hit the lens plane somewhere here, and then it becomes parallel. So wherever the image forms, I can draw one more ray to show where that image will form, and that other ray will be this guy going parallel to the optical axis, turn and go through the far focal point, and they will meet beyond the slide. So the image will be magnified and farther away from the lens plane as the object is. And then as a third example, if I move the object farther from 2F, so move it farther away and put it somewhere here, then the line that goes through the near focal point will hit the lens plane above where the previous line hit. So now the image will be smaller and it will form at a point where these two intersect. So it'll be somewhere there. So I know I went through that fairly quickly, but you can think about that for yourself, and we will do some more examples of that in class. But you can see that all of the image properties depend on the position of the object. And this property that the size and position of the image depend on the object's position or distance from the lens plane leads to something called the magnification equation. And that is written as m equals minus s prime over s. So let me go back here. We had h over s equals h prime over s prime. I can rearrange that to write h over h prime equals s over s prime. And so magnification is simply the height of the image compared to the height of the object. So it's this left-hand side. And so I can write that equal to the right-hand side since those two things are equal to each other. And the reason we add this negative sign is so that this equation can tell us the orientation of the image. So let me give you some conventions in using this equation. So the object distance s is always positive. The image distance s prime is positive for real images and negative for virtual images. In this case, the image is real, so s prime will be positive. And then the resulting sign of the magnification will tell us the orientation of the image. So if m ends up being positive, then the image will be upright. And if m ends up being negative, the image will be inverted. In the 3 cases we have discussed here, s is always positive. S prime is positive for all these 3 cases because in every situation the image is real. So both s and s prime are positive, which means m will result to be negative because of the minus sign over here. And so whenever we have real images, we will always have inverted real images. That's what this equation tells us. All right, the next thing is, can we have a virtual image? So far, all 3 examples we talked about had different sizes and different positions of the image based on the object position, but they were all real and they were all inverted. Can we have a virtual image for a converging lens? Well, let's take a look. So here is the converging lens, and now I have moved the object between the focal point and the lens plane. So here is my S, and in this case, S is less than F. So let's do the ray tracing for this. The first ray is the one that goes parallel to the optical axis, and that bends and goes through the far focal point. The second ray of light we discussed is the one that goes through the near focal point. So in this case, that ray of light will be going this way, and that's a useless ray of light for what we are talking about here. It does not pass through the lens at all. So let's move on to the third one. The third ray of light will be going straight through the center of the lens and continue straight without bending. So it'll go like that. And so now we see something interesting. These 2 rays of light are diverging. You can see that they keep getting farther and farther away. So they're never going to meet on this side of the lens. because they're diverging. And by the way, the third ray of light that we use for the near focal point is, even though this particular ray of light going through the near focal point never hit the lens, we can think of a ray of light that goes from the tip of the object as an extension of that. There will be a ray of light going this way as well, which appears to come from the near focal point. So this would be a real ray of light that'll go that way, and that will become parallel to the optical axis. So here's my third ray. So now we can see that all these three rays of lights are diverging and they're never going to meet on that side of the lens. So we do the same trick as we did for the mirror. We extend them backwards behind the mirror, or in this case behind the lens, and we see that these two rays intersect at a point, which is where the image of the tip of the object should be. Just to check, we use the third line and make sure that it goes through the same point, and it does. So my image is going to be over here. So when I have the object between the focal point and the lens plane, we get a virtual image. Even though it's a converging lens, we get diverging rays of light. Remember, we said a converging lens is called as such because parallel rays of light converge. In this case, these three rays of light are not parallel, so they don't have to converge, and they actually don't. So now if I were to list my image properties, it is virtual. Why virtual? Because there are no real rays of light here. The image appears to be at that point, but there is no rays of light that exist there. It is upright, and then in terms of distances and sizes, it's magnified. It's larger than the object, and it is farther than the object's distance on the same side as the object is. So let's check the magnification equation in this case. M was minus S prime over S, and we said S is always positive, but we said S prime is positive for real images and negative for virtual images. So in this case, S prime would be a negative number, and that negative number will cancel the negative that's in front of this right-hand side. So this M will result to be a positive number, and a positive M tells us that the image is going to be upright. So that checks out. All right, the last thing we want to talk about in this video is the thin lens equation. And it's an equation that uses a little bit more of the geometry that we talked about to set up this relationship. 1 over S plus 1 over S prime equals 1 over F. So it relates the object distance and the image distance to the focal length of the lens or a mirror. So even though it's called a thin lens equation, this works for mirrors as well. So once again, to use this equation, S is always positive, same rule as before. S prime is positive for real images and negative for virtual images. And F is positive for a converging lens or mirror and negative for a diverging lens or mirror. All right, in this slice of physics, we looked at ray tracing image properties. We saw that converging lenses can produce real inverted images or virtual upright images, and which could be either magnified, shrunk, or the same size. All of that depended on the object distance from the lens plane. We discussed the magnification equation that related the size of the image to the position of the object and the image, and then looked at the thin lens equation that related the object and image positions to the focal length of the lens or mirror. Thank you.